think about it in terms of if P then Q, the truth of that, alright, so this is true, this is true, this is true, and this is false. So this is equivalent to not P or Q. Because if P is false, this will be true. If Q is true, this will be true. Otherwise it will be false. So this and this, I think you can interchange. So if hypothesis then conclusion, that's true if the hypothesis is false or if the conclusion is true.
So probably the easiest answer to number 4 is going to truth table.
Number 2. Yeah, truth table is simpler, but why not do it both ways and see what you come up with. It's like twice the fun for the same price. You said number 4 is tricky?
Yeah.
So what does number 4 ask?
Go back to it. So it's saying for each of these arguments, determine whether the argument is correct or incorrect and explain why based on the rules of inference.
So is there a particular one that's, or is it just the general nature of those?
When did we cover the rules of inferences? Like, what day was that?
Modus ponens, modus tonens. I think it's in the tags on the videos.
They don't call it rules of inference in the book.
No. They don't call it modus ponens either. But it's around page 58.
59.
The laws of logic, maybe.
Well, even just starting with the first one, I guess there's no direct rule that addresses this is true, this is false, therefore this is false. And I think my brain is short circuited.
All right, let's look at these. This homework 2 we're up to?
Yes.
Okay. I'll post homework 3 tonight or tomorrow. All right, for each of these arguments, oh yeah, the movies and the cars. For each of these arguments, determine whether your argument is correct or incorrect and explain why based on the rules of inference. All right, so. The trickiest part on these is figuring out what your propositions should be so that we can do things like hypothetical syllogisms and so on. So let's look at question A. Everyone enrolled in this class lives in Vancouver. Lisa does not live in Vancouver. Therefore, Lisa is not enrolled in this class. Okay, so let E be the proposition that you're enrolled in this class, or someone is enrolled in this class. V is the proposition that you live in Vancouver. So if a person is enrolled in the class, they live in Vancouver. Bless you. So that's saying if E, then V. Okay, that's a premise. Lisa does not live in Vancouver. So we're told if E, then V, and we're also told not V. That's a premise. the conclusion from here is Lisa is not enrolled in this class. In other words, not E. Is this true? If we can prove that given this and this follows logically, then this is a valid argument. But if we know that even given this and this does not have to be the case, then this is an invalid argument. So E implies V and not V. Can we conclude not E?
I mean, just looking at the problem itself, if you drew it out with like a Venn diagram, for example, you would see that the statement is true, I think. So, although I'm not sure how to prove that exactly. So I'm expecting it to be true.
Isn't this just modest tolerance?
Yeah, so there's a fancy name for this.
What was it? Indirect reasoning?
So modest Tollens indirect reasoning. Right, this is one of the rules of inference that we were given. So page 59, indirect reasoning. If P then Q and not Q, therefore not P. So this is a valid argument, right? If you're a dog, you like bacon, you don't like bacon, therefore you're not a dog. Because if this were not the case, you'd have to have E, and if you have V, you have to have V, and you're told not V. So that's a correct argument.
I see I was approaching it in the wrong direction.
Okay.
What you said the engineer was going in?
This is indirect reasoning. Or modus tollens.
So if we had just said that it represented an example of indirect reasoning, that would be just fine.
I would want to see the propositions and how you broke that premise down into those pieces. That's the explain why based on. So yeah, I want some more detail than just the name. Given that, do you want to try B and C on your own?
I think I'll be okay with there, but
Okay. Like I say, I think the trickiest part is coming up with the propositions. So for here, I might say a car is a convertible and a given car is fun to drive. And for this one, I would say you like a movie and a movie is really good, maybe. All right, other one works. All right, let's go back to number theory things. So we were talking about divisibility and factors and multiples and things like that. And I wish there wasn't red marker on this board. There it is.
You could try using the spray.
I could, but that sounds labor intensive.
I think of why
The magic rag is missing, which is even more of a bummer. I'll get it between classes. So we were talking about congruence, modulo something. So A is congruent to B modulo M. And what was our definition of that statement?
if A and B when divided by M have the same remainder.
A and B have the same remainder when divided by M. also say A minus B is divisible by M.
Bless you.
And that absolves us of having to figure out remainders with negative numbers. So if their difference is multiple of M, then we can say they're congruent. And I think I ended up by noting that, for example, if we work modulo 7, 23 is congruent to 16, is congruent to 9, is congruent to 2, is congruent to negative 5, is congruent to negative 12. And there's an infinite number of integers that are congruent to each other, modulo 7.
Are we assuming A is bigger than B?
Nope,
or no?
doesn't have to be. But we are assuming M is bigger than or equal to 1, usually bigger than or equal to 2. So we don't want our modulus to be negative, but A and B could be negative, positive, 0. So an infinite number of things are all congruent to each other modulo 7. There's another infinite family of things which are congruent to each other modulo 7, but a totally different set of integers from here. And there's a third set. And how many sets of these infinite families of integers can I find that are unique from each other?
Isn't it 6?
It's going to have to be 7.
7.
Because we include 0. So there's actually 7 of these infinite families. So we can take the infinite set of integers and break them down into just 7 things, where each thing is an infinite subset of the integers. And we can identify these sets in different ways. We could just call them A, B, C, D, E, F, G. But the way we identify these sets is we find the unique integer, which is bigger than or equal to 0 and less than our modulus, which is 7 in this case. So we've taken our infinite set of integers, we've broken it down to basically 7 objects. And we can call those objects 0, 1, 2, 3, 4, 5, 6. And each of those objects is all the numbers that are congruent to that one particular number, 0, 1, 2, 3, 4, 5, or 6. So we can make a subset of the integers. In this case, we'll call it Z7. That consists of these 7 numbers. And we can do algebra on this. As long as any time we do algebra, we always come back and remember that we're working modulo 7. So if I'm working strictly over Z7, I can say 2 plus 3 equals 5. I can say 2 plus 4 equals 6. But if I try to do 3 plus 4, that's equal to 7, but 7 is not one of these elements. But 7 is congruent to 0, so 7 and 0 are the same thing. So 3 plus 4 is equal to 0. And 4 plus 4 is 8, which is congruent to 1. 8 is congruent to 1, so 4 plus 4 is equal to 1. And we can do algebra like this. And it's a bit peculiar looking at first, maybe. But any time that we add 2 of these numbers, we're going to get an integer. And if it's bigger than 6, we just reduce it modulo 7. and we'll get something that's, again, one of these integers. So we can say this is closed under addition. When you add two numbers from this set, we get another number from this set. As long as we do our addition modulo 7. So sometimes you'll see this plus sign with a little 7 underneath it to say it's addition modulo 7. But we'll just assume that's there. And you can take a whole course that studies algebra of modulo systems like this. And it's actually a fairly fascinating field in itself. Well, let's look at some of what we get for this. So let's keep working over Z7. So we have addition. We have a 0 element. 0 plus any number is going to be equal to that number. That's the definition of a 0 for addition. You can add it to something and you get back your something. If we have a 0, we can ask, do we have negatives? Is there a 3 plus something, which gives us 0? And there is 3 plus negative 3, although negative 3 is not part of that, but negative 3 is congruent to 4. So 3 plus 4 equals 0. So 4 is actually negative 3. It starts to sound a little like 2's complement, perhaps, because it is. So every number has a negative. Negative 1 is 6. Negative 6 is 1. So we can do addition, we can do subtraction. So 4 minus 3 is 1. What is 3 minus 4? Yeah, it's negative 1, which is also 6. And the quick way that I do these, 3 minus 4 equals negative 1. If I've got a negative number, just start adding 7 until you get something between 0 and 6. If you got something bigger than 7, start subtracting 7 until you get something between 0 and 6.
It's almost like an angle, like how like it can be 270 or negative.
Yes, exactly.
If you were working with something like this in programming, is there like a wrap value function in C?
Not that I can think of off the top of my head, but there are modulus operators which might make this doable. And if you're working modulus power of 2, there's all kinds of cool tricks you can do, which is often what we'd be doing. So yeah, it's very much like an angle. This is 60 degrees, but it's also 300 degrees. Or maybe negative 300 degrees because we went clockwise. And negative 360 are congruent to each other mod of 360. The way I first learned this was with clocks, and it doesn't quite work because we usually start with 1. But if you think of the 12 as 0, if it's 11 o'clock and you go forward 3 hours, instead of 14 o'clock, you get to 2 o'clock. So clocks are basically a modulus 12 counting system. Mod 7 you could think of as days of the week. If it's Tuesday and you go forward 6 days, you get to Monday. And if you assign numbers to those, you can do that with modulo 7 addition.
Can you go into how do we get from negative 1 to 6 for 3 minus 4?
3 minus 4 is negative 1, which is also congruent to, right? If you add 7 to something, it's going to be congruent modulo 7.
Okay.
So
it's
negative 1 plus 7
negative
is 6.
Okay.
Yeah. Right, I could add another 7, this is also congruent to 13. I could subtract 7, this is congruent to negative 8. So you can go back and forth all day.
But isn't the whole idea of like adding and subtracting 7 to get a number that's within our...
Yeah, you want to get a number greater than or equal to 0 and less than 7. So how does modular arithmetic compare to regular arithmetic? We have commutativity. A plus B equals B plus A. Because we're basically doing regular integer arithmetic, we're just reducing modulo 7 at the end. We have commutativity, we have associativity, we have all the usual things. We have this 0, an identity element for addition. That's math lingo. And we have additive inverses, what we call negative numbers. For any number, we can add something to it and get 0 as a result. We also have multiplication. So 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8, which is actually 1. What's 5 times 5? 4. It's 25. If you subtract 4, you get 21. That's a multiple of 7. Or 25 minus 21. So we can do multiplication. Can we do division?
Should be able to. Same as multiplication.
Kind of. This gets really confusing quickly, though. So what is 5 divided by 2? 2.5? No. But in fact, we can do this. But we have to be a little careful what we mean by division. When we say 5 divided by 2 equals x, we're looking for some number that when we multiply by 2, we get 5.
There's a lot of different numbers we could use for that.
Like, I'll take 1. We're all doing the same thing
13.
right now.
13.
13. So 2 times 13 is equal to 5. Good.
The unfortunate thing is I'm above 7 when I did that.
But what?
I was above 7 when I did that because it's 13.
So if we wanted to stay below 7, 2 times 6 is equal to 5. So in some sense, 5 divided by 2 is equal to 6, which is a little weird. So I'll put one question mark after it. And we don't actually talk about division directly like this usually, but we can talk about inverses. We can talk about 1 divided by something. So 1 divided by 2, which we would write as the inverse of 2, it's something that when you multiply by 2, you get 1. So what can you multiply by 2 that gives you 1 modulo 7? Integer. So what can we multiply 2 by to give us 1? 4. So the inverse of 2 is 4. Because 2 times 4 is 8, which is 1. So 2 has a multiplicative inverse, which is equal to 4. Ergo, 4 has a multiplicative inverse, which is 2. One is its own inverse. 1 divided by 1 is 1. Well, that's kind of warm and fuzzy. Three gets multiplied by 5.
I probably missed something, but couldn't we multiply 2 by something else and still get it equal to 1?
Like? I think the answer is no, but
No, you can't. I see how that works.
yeah, you could multiply by something bigger than 6, but it would turn out to be equivalent to 4.
Wait, why does 2 to the negative 1 equal 4? Can you?
Because 2 times 4 is equal to 1. Right, this just means 1 over 2. And 1 over 2 equals 4 means that 2 times 4 is equal to 1.
In the context of... No, okay, never mind.
Yeah, we're all modulo 7 today.
Right, that's what I meant, yeah, in the context of that. That's
Yeah.
That's what I thought.
Is there anything special about 7?
Yeah, maybe. So we have multiplicative inverses, which means we can do something like division. We don't actually call it division. It's always multiplication, but we can find these things that when we multiply 2 of them together, we get back to 1. Is there an inverse for 0? Can we multiply 2 non-zero things and get 0?
Yeah.
What would be an example?
Wait, no, we can't.
7 is 0. So no, it turns out we can't. Which is nice, because when we do algebra, if, 5x equals 0, we immediately say x must be 0, right? But we can only do that in regular algebra because we know if 2 things multiply to 0, one of them has to be 0. And that turns out to be the case here also. But let's totally change it up, and let's look at Z6. So now we're looking at numbers bigger than or equal to 0 and less than 6. So we still have addition and subtraction. And we still have multiplication. So 3 times 3 is equal to what? We're in Z6 now.
3.
It's equal to 9, which is equal to 3. What about 3 times 4?
4. 2. 0?
It's 12, which is equal to 0. So now suddenly we have non-zero things multiplied together, giving us 0. That's a totally different kind of universe. And all the things that we're used to doing in regular algebra suddenly break down. Because a times b is equal to 0, but neither a nor b is 0 itself. And that gets us into some strange areas. So the inverse of 1 is just 1. 1 times 1 is 1. What's the inverse of 2? So what can we multiply 2 by to give us back 1 modulo 6? Well, 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 0. 2 times 4 is 2. 2 times 5 is 4. We don't have one. So this does not exist. So 2 does not have a multiplicative inverse in Z6. So sometimes these modulo systems, modulo M, sometimes they act like systems we're used to, sometimes they don't.
Does there a pattern to that?
Is there a pattern to that?
I think if they are prime numbers,
Yeah. If this is prime, it acts like Z7. We have multiplicative inverses, and two things have a product of 0 only if at least one of them is 0. If M is composite, we get something very different.
Wait, Z is all integers, right?
Z is all integers. Zm is integers modulo M. So it's M infinite subsets of integers. And so this is maybe one of the first cases where prime numbers start to come up as something other than just kind of an odd exercise. They actually correlate with fundamental differences in the nature of what we call these rings of integers, modulo M. And when M is composite, we see quirky behavior, like two non-zero things multiplying to give us 0, and a lack of inverses. So let's play around with primes a little. And primes are kind of quirky things themselves. So prime number, a number that's only divisible by itself in 1. We don't consider 1 to be prime, but we start from 2. 2 is prime. 3, 5, 7, 11 are prime. 9 is not because it's divisible by 3. Even numbers bigger than 2 are divisible by 2, so they're not prime. And one of the things that we've alluded to was this question of how many primes there are. And the Greeks figured out there were an infinite number of primes. And it's fairly easy to show that with an indirect proof or a proof by contradiction. So we can prove this in a minute or two. So suppose that this is not the case. Suppose there are only finite many. Well, we can make a set of all the possible prime numbers then. So let's call these P1, P2, P3, P4, all the way up to Pn. So this equals a set of all primes. And if we assume this, we can find a contradiction pretty easily. So the contradiction is make a new number x, which is the product of all of these plus 1. So this is divisible by P1. Agreed? If I add 1 to it, it cannot still be divisible by P1. In fact, if I add 1 to it, when I divide this by P1, I'm going to have a remainder of 1. Because x is equal to P1 times something plus 1. So P1 does not divide x. And this expression is also equal to P2 times P1, P3, P4, Pn plus 1. So when I divide x by P2, I'm going to have a remainder of 1, which in particular means P2 also does not divide x. And I can do this for all my known primes. And I can show that x is not divisible by any of those prime numbers. Still with me?
So that means that x is another prime that was not in the set.
So either x is prime and we know that x has to be bigger than Pn because it's Pn multiplied by a bunch of stuff plus 1. So either x is a prime and it's not contained in this set, which is a contradiction, or x is not prime, which means it's divisible by something, but it's not divisible by any of these primes. It's got to be divisible by a prime that's not in this set, which is a contradiction again. So either way you have a contradiction. Your only conclusion is that your hypothesis must be false. So there must be an infinite number of primes. And that's a good thing, because the internet wouldn't work otherwise. At least not the way it works today.
Yeah, I was going to say, it could be another one.
It could be another way. I think it's based on dogs and bacon.
Of course. It's
Yeah.
always good stuff to document.
Absolutely.
Secure bacon.
Yeah. And primes are fascinating in their own way. I've always been a geek on primes. My Steam name's Prime Minister 37. There's all kinds of things about primes, and again, when we talk about number theory, problems that are really easy to describe but really difficult to answer. And primes are a good source of that. So this is one that's actually pretty easy to answer. But there are other questions that are more elusive, and we'll talk about some of those another day. How many people here are familiar with cicadas?
The insect?
The insect. They're about this big. They look like crickets on steroids. They have big red bug eyes.
They scream.
And they scream. Has anybody ever been around a cicada brood hatching on its periodic cycle? So back east, there's a 17-year cicada. And every 17 years, all these cicadas hatch. They mate, they climb up in trees, they drop down in the ground, and their larvae bury into the ground, and they sit there for 17 years. And they mature slowly, and after 17 years, they all come out again. So every 17 years, you get this explosion of millions, possibly billions of cicadas everywhere. And the road is just green and squirming and making noise. And it's kind of disgusting. And you go in the woods, and it's like genuinely painful, the volume of it. It's really impressive if you ever get a chance. And there's this 17-year cicada. There's also a different variety that's a 13-year cicada. And you can speculate about anything, but there's speculation that the fact that these two numbers are prime is not a coincidence. Because if these cicadas came out every, 2 years and 3 years, they would overlap pretty frequently. If you had something that was a common multiple of both of these populations would both emerge that many years apart. But because these are both prime numbers, they're only going to both appear every few hundred years. And you can argue that perhaps this is a survival mechanism to reduce competition so that one brood appears and it's unlikely the other brood will be hatching at the same time. And you start to find prime numbers popping up in all kinds of interesting places, a lot of places in nature, a lot of places in physics. And there's some really weird connections when you start looking into string theory between very large prime numbers and things that have no business dealing with prime numbers. So it's a interesting area, to me at least. And they pop up in computer science a fair amount as well.
Which applies to prime being the same way in different numbers in different bases, in base 2, base 3.
Yeah.
What happened?
Yes, and thank you for reminding me. If we work over Z2, where our only objects are 0 and 1, does that look familiar? We can start drawing some correlations here between modular arithmetic base 2 and Boolean things. And it's not perfect unless you do a little bit of work, but Boolean algebra is another example of an algebra. Arithmetic over modulo 2 systems is another version of algebra, and they're very close to each other, actually. Let me throw out another oddity, maybe to leave you with. This is called the prime number theorem. It's got to be good, right? So here's a question. How many primes are there less than or equal to some number x? So let's just say P of x means the number of primes less than or equal to x. What do you think P of x is equal to? It's clearly less than x. We can probably say for a big enough x it's less than x over 2, because the number of primes, most of the primes are going to be odd. So we're looking for primes up to 1,000,000. There's not going to be any more than 500,000.
Well, isn't it could be less than the square root?
It's going to be less than the square root. So we're starting to make some good guesses on what px might be, or at least some bounds on it. It's going to be bigger than something. So it turns out, and this is an interesting proof, turns out as x gets bigger and bigger, P of x gets really close to the natural log of x. It always comes back to the natural log. So this ratio, number of primes less than or equal to x divided by the log of x, that gets closer and closer to 1 as x gets bigger and bigger. And this has been proven. It's called the prime number theorem. So we have a tie-in between natural logs, and they're called natural logs because they pop up all over in nature. Natural log is logarithm base e. E is growth rates of all kinds of processes, population growth, bacteria growth, and so on. And somehow that's related to the number of things that aren't divisible by other things, which seems a little bizarre, but in a good way. All right, I'll leave you with one more thing to think about, and we'll continue with this tomorrow. This is unique factorization. If I pick a number that is not prime, I can write it as a product of primes. For example, 100 equals 10 times 10. 10 is equal to 2 times 5. I can write this as 2 squared times 5 squared. 2 and 5 are both prime. I can write 48 as 2 cubed cubed, 2 to the 4th times 3. I can write 75 as 3 times 5 squared. So any number that's not prime I can write as a product of prime numbers. The cool thing is, this is unique, other than rearranging the order of these terms. So this is 2 squared times 5 squared. I can't rewrite it as a product of any other set of prime numbers. So this is called the unique factorization theorem. And it's true for integers in our world. It's not true for other kinds of integers. And that has a long history, going back to Fermat's last theorem and before that. But we have unique factorization. So when you have an integer, you can always break it down into a product of primes. And we're going to use that critically when we talk about crypto systems on Thursday. All right, I'll leave you with that. We'll talk about some applications of modular arithmetic to computer science tomorrow, and then we'll start talking about cryptography and public key ciphers.